Derivative part 2, the sequel. All right, so we did some of this stuff already, right? We did these. Now we're going to move into basically the pretty much graph ideas. We're also going to do related rates though. I'm going to spend a lot of time talking about graphs and how the f's and the f primes and the f double primes are all related. Okay, so let's start looking at just basic ideas. Function is increasing when the derivative is positive, and it's decreasing when it's negative. Okay, that shouldn't be new at this point. Function is concave up when the second derivative is positive and concave down when it's negative. Since the second derivative is the first derivative of the derivative, we can extend concavity. Okay, second derivative, first derivative of the derivative. Okay, so if the derivative is increasing, I'm going to actually zoom in so I can write this stuff. F prime is increasing. That would mean that f double prime has to be positive. Right? Well, if f double prime is positive, f of x must be concave up. So if f prime is increasing, I can know that f is concave up. So I don't just have to rely on the second derivative to get concavity. And if I know that f prime is increasing, it's concave up. Similar reasoning, if f prime is decreasing, then f is concave down. So that's really useful knowledge to have. Okay, graphs and extrema. We got critical points are when the derivative is equal to 0. We might have a max or min there, as long as the derivative changes sign. So we get a max if it goes from positive to negative, and we get a min if it goes from negative to positive. I always just think about it in my head. Okay, positive to negative. Okay, there was a max. Inflection points happen when the second derivative changes sign, with similar reasoning that we had on the previous slide. If the first derivative changes direction, then the original function will have an inflection point. It'll change concavity. Okay, last little bit, we got our candidates test. Gives us absolute extreme on a closed interval. I don't have an example of a candidates test question in here, but I will in a later video. But basically all you do is you plug the endpoints and the critical points into the original function, see which one's biggest or smallest. That's sufficient justification. That's the thing where we make the table value, the table of values. The first derivative test gives the relative extrema, find critical points, and determine if the derivative changes sign there. So that's where we make the sign chart. But remember, AP graders will not look at your sign chart. It is not a sufficient justification. You have to say the derivative changes sign at this particular x value. Or it's a positive to negative if it's a max. Negative to positive if it's a min. You have to say that. You have to write a sentence. Don't call it a paragraph. It's a sentence. But you really do have to write it. It's very important that you do that. Okay, I think, yep, there we go. We got some problems. 3 graphs labeled 1, 2, and 3 are shown in the above. One is the graph of f, one is the graph of f prime, and one is the graph of f double prime. Which of the following correctly identifies each of the 3 graphs? Okay, this question is a little cumbersome. What you want to do is you want to identify one graph and just say, okay, you're f now, and see if the others match. And then if it doesn't, now you know that one's not f. So I'm going to go in order. I'm going to look at 1 and say, okay, 1 is f. So that means up until about here, its derivative must be negative. Okay, well, 2 doesn't do that. 2 is positive for a while. And 3 starts off negative, but it's not negative for long enough. Oh, I guess 1 isn't f then. So I just ruled out a. Well, let's try again. Oh, my pen's fighting me now. It's just like in class. Now I'm going to say you're f. So it should be, the f prime should be negative just for a teensy little bit. And then it'll be positive for a teensy little bit. And then it'll be negative all the way up until here. So I'm going to look and see, does 1 do that? No, it doesn't change sign quickly enough. Does 3 do that? Well, it's negative, and then it's positive, and then it goes negative again for a while. I kind of think that's f prime. That's looking pretty good. It's looking kind of like 2, 3, 1 to me. I just need to verify that number 1 is in fact f double prime, so I need to look at the concavity. So it looks to me like it's concave down, or concave up until then, and then it's concave down until about, well, I don't know, there. So then I would need the second derivative to be positive and then negative. Positive, negative, positive. That looks great to me. I'm going to go with C as my answer. The derivative of the function f is given by f prime of x equals negative x over 3 plus cosine of x squared. At what values of x does f have a relative minimum on the interval 0 to 3? Okay, I'm looking for relative minimum. That means I need to know when the function changes sign. So I need to find when the function is 0. So I need f prime to be 0. I have no idea how to find when that is 0. Luckily, this is a calculator question. Okay, so I've got the graph now. And what I like to do is change the window so I'm only looking at the relevant x values. And I change the y values too. If I know I'm looking for a 0, I make it as small as I can because I don't need to see much. I just need to see around 0. That's why you see I've got negative 0.5 and 0.5 is my min and max for the y's. That's what I like to do. So now I know I'm looking for a relative minimum. So this is the graph of f prime. I need to go from negative to positive. Well, that happens right here. So now, wouldn't it be nice if I knew what x value that was? Your calculator will find the zeros for you. Don't trace it. It's not going to be close enough. Go into the menu and actually use the calculate zeros feature, like I did. I got 2.3715, rounds to 2.372. I am satisfied with that answer. The second derivative of a function g is given by g double prime is that thing. For negative 5 to 5, on what open intervals is the graph of g concave up? Well, g is concave up when g double prime is positive. Man, I sure wish I knew when that was positive. I'm on the calculator section. Let me graph it. Okay, this is g double prime. It's positive starting right about there. And then it never stops being positive again. So I just need to find that 0. Again, don't trace it. Use the 0 feature in your calculator, like I did. So starting at negative 1.016, it's positive, and it stays positive for the rest of the interval. That's my answer. Okay, now I'm going to look at the graph of f prime. The derivative of the function f is shown above. Which of the following could be the graph of f? Okay, first thing I'm going to do, I see 4 answer choices at a time, so let me try and eliminate something quickly. F prime exists for all x values from 0 to 6. So that means there should be no cusps, corners, discontinuities, vertical tangent lines in my original function f. Well, I see discontinuities, I see discontinuities. Can't be it. So it's either A or B. Well, f prime is negative up until 1, right? So that means f should be decreasing until 1. Well, they both do that. From 1 to 2, from 1 to 3, in fact, f prime is positive. So that means it should be increasing. Well, they both do that too. From 3 to 5, f prime is still positive. So f should still be increasing. But B, answer choice B, has it decreasing. So that's wrong. So again, going through that just kind of quickly, I'm just looking at the signs of the derivative that tells me if the function is increasing or decreasing. For this problem, 3 was the giveaway. I didn't have a max or min there. I didn't turn around. So it must be A. Okay, the derivative of a function f is given by f prime is that thing for 0 to 9. On what intervals is f decreasing? Well, f is decreasing when f prime is negative. Man, I sure wish that was negative. Wait, I'm on the calculator section. Graph it. I need it to be negative. Again, I adjusted my window. I see a little spot here, and I see a little spot here. So there are 3 zeros I need to find. I need to find this 0, and this 0. Again, that thing that I said more than once. Do not just trace it and think that's close enough. You need to actually calculate the zeros, like I did. So it looks like from 0 to 0.633, and then 4.115 to 6.916. A. Man, wouldn't that have been embarrassing if I got it wrong? The graph of function f is shown in the figure above. For which of the following values of x is f prime positive and increasing? Okay, f prime positive I can get pretty easily. I just need to find spots where it's increasing. It's the f prime increasing. That's the part that's a little weird. F prime increasing. We've done this before. We did this a few slides ago. That means f double prime is positive, which means f is concave up. So I'm looking for a point where the function is both concave up and increasing. That'd be E. It's the only point that they gave us where it's both concave up and increasing. That's it for graphs and stuff. So we're doing related rates and implicit differentiation now. I know it's your guys' favorite. You differentiate a variable with respect to some other variable, you have to multiply by dy dx, or maybe dv dt or something like that. It's just, you have to multiply by the derivative. Related rates problems use this so much, it's basically where all of this work comes from. But what the related rates problems do is they talk about how like volume and height both changing is how they affect each other as time goes on. But it's how one thing's change over time causes another thing's change in time. Wow, the grammar in that sentence was horrible. Oh well, I teach math. X plus 2y times dy dx equals 2x minus y. What is the value of d squared y dx squared? So that means second derivative at the point 3, 0. Okay, there's a bunch of different ways to do this. What I like to do is I like to move that x plus 2y over now, and I'll just use quotient rule. So that means, let me zoom in. I know I'm going to need a lot of space. dy dx equals 2x minus y over x plus 2y. So I'm going to start taking the derivative of this. So d squared y dx squared, remember low d high, high d low, low over low squared. So x plus 2y times the derivative of 2x minus y. So that's 2 minus the derivative of y is not 1. The derivative of y is 1 times dy dx because I'm not differentiating with respect to y. So it's going to be 2 minus dy dx minus the top, 2x minus 1, times the derivative of the bottom. So that's going to be 1 for the derivative of x plus 2 dy dx all over x plus 2y quantity squared. Okay, so all I have to do now, which that sounds like, oh, that's all you got to do? X plus 2y, 2 minus all this stuff. I need to plug in the point. They gave me the point 3, 0. But wait, I don't know what dy dx is here. Good news. You do know dy dx. It's right here. Plug in the point 3, 0 to that, and you'll know what to plug in for dy dx. So this is 2 times 3 minus 0 over 3 plus 2 times 0. That's 6 over 3. That's 2. So that's dy dx at this point. So I'm going to plug in 3 for all the x's I see, 0 for all the y's, and 2 for all the dy dx's. So this is going to be 3, just 3 because 2 times 0 is 0. 2 minus 2 minus 2 times 3 is 6, minus 0 is 6. 1 plus 2 times 2, all over 3 plus 0 squared. So this part goes away, because 2 minus 2 is 0, and then minus 6 times 5 is negative 30 over 3 squared is 9, which simplifies to negative 10 over 3. So A. It's a little bit of a nightmare to do that problem. These implicit differentiation problems are a little bit of a mess, but just all the big thing is just remember, when you differentiate something that's not the same variable, you multiply by dy dx or something to that effect. All right, an ice sculpture in the form of a sphere melts in such a way that it maintains its spherical shape. The volume of the sphere is decreasing at a constant rate of 2 pi cubic meters per hour. At what rate in square meters per hour is the surface area of the sphere decreasing at the moment when the radius is 5 meters? Okay, this is a related rates problem. It's going to use implicit differentiation. So I need ultimately the rate of change for the surface area. So what I'm going to do is I'm going to take that S equals 4 pi r squared, and I'm going to differentiate it. So that's going to be 8 pi r, but I'm differentiating with respect to t, so I'm going to need to do dr dt. Well, I know the radius is 5. Oh, no one gave me dr dt though, did they? I'm going to have to do something to solve for it. What I'm going to do is I'm going to look at the volume formula. If I take the derivative of that, that'll put a dr dt in its equation. dv dt equals 4/3 times 3 is just 4 pi r squared dr dt. Well, I know r and I know dv dt. dv dt is this right here. So I can use that information to solve for dr dt and plug it back into the blue. So I'm going to do negative 2 pi equals 4 pi, 5 squared is 25, dr dt. So 4 times 25 is 100 pi, so negative 2 pi over 100 pi is equal to dr dt, which is equal to negative 1 over 50. So now I can just plug that into the blue equation and I'll have my answer. So that's 8 pi times 5 times negative 1 over 50. So that's 40 pi, which simplifies to just 4 pi over 5. You might be wondering, where'd the negative go? Well, they said, at what rate is it decreasing? So that implied the negative sign. The negative sign would be redundant. So we didn't need it both times. All right, last one. The height of the water in a conical storage tank shown above is modeled by a differentiable function where h of t is measured in meters and t is measured in hours. At time t equals 0, the height of the water in the tank is 25 meters. The height is changing at the rate h prime of t equals meters per hour for 0 to 24. When the height of the water in the tank is h meters, the volume of the water is given by volume equals 1/3 pi h cubed. At what rate is the volume of the water changing at time t equals 0? Indicate units of measure. Okay, so I want dv dt. I want the change in volume over the change in time. So I'm going to take that expression that they gave me, and I'm going to do dv dt. So that's going to end up giving me pi h squared dh dt. Well, remember, dh dt just means derivative. Well, this also means derivative, right? They said at t equals 0. So I need to plug t equals 0 into the h prime, and I know that when t equals 0, the height of the water is 25. So now I've got pi times 25 squared times 2 minus 24e to the 0 over 4. Right? So plugging in 0 for t gives me 24e to the 0 over 4. So that's 625 pi. 24e to the 0, remember, is 1, so that's 24 over 4. So that's 2 minus 6, so negative 4. And at this point, I'm going to my calculator. Please don't be disappointed in me. And that's equal to negative 7,853.98. Now it says indicate units of measure, so we got to make sure we do that. Volume is the height is measured in meters. Volume is a cubed thing, so it must be meters cubed. And it said that the h prime of t is meters per hour, so this must be meters cubed per hour. And that kind of looks like a toothbrush. That's it for this video, which kind of wraps up derivatives. Remember, this is not exhaustive, but it is a lot of things that come up very often, so I want to make sure I hit things like this. We've got integrals and we've got particle motion left. Make sure to get those as soon as we can.